Hey there, I'm Heather, and I'm going to do hopefully a very quick overview of some of the main seismic processing steps that we use in seismic reflection data to prepare our data for seismic interpretation. So let's get started. All right, so processing is very complex, and I'm just going to go over some very quick basics. So I want to mention a few references for more details. So both of these textbooks, the Oz Yilmaz's Seismic Data Processing book is really good, and so is Chris Liner's Elements of Seismology textbook. And so I'm going to start off by stepping through an example from Fred Schroeder, who was retired from Exxon when he made these slides, to help you understand the general workflow, and then we'll go back through the steps in just a little bit more detail. So kind of a two-step lecture here. All right, so we start off with our marine shot record. So I just talked about seismic acquisition. We've got our original shot record is shown here. And what you can see is that we've got our receivers. For our shot record, we can see the direct arrival and we can see the reflection. And so one of the first steps that we're going to do is we're going to try to arrange the data in a way that the shots traces are gathered at a common midpoint. Okay, so that common midpoint is that one kind of cube in the subsurface where we're going to take all the traces that bounced there and we're going to put them together. And so this gives us our common midpoint gather. And then once we have that common midpoint gather, we want to take it, and one of the things you'll notice here is that there's a little bit of a curvature to it, and that's because the common midpoint gather is arranged where, with my pointer on, here we're getting larger distances, so larger angles. And so in the higher offset, these waves are traveling further in the subsurface, so they arrive a little bit later. And so it gives us that kind of hyperbolic look to the shot gather, the CMP gather, sorry. All right. And so once we've got the CMP gather, we want to be able to stack it. So we have to figure out a good velocity that will help flatten the gather at this point. And so typically we can use different, test out different velocities that we may have until we get a velocity that's kind of just right. And it's been corrected properly. And so there the reflection won't curve too much. And let's see. And so in this top case, the velocity is a little bit too slow because we've kind of got the hyperbola going downwards. If it's correct, it's flat. And if the velocity is too flat, it kind of curves up. So we first need to get that good velocity model. And then once we have the velocity model and we've corrected the midpoint gather, we can then sum them together. So we can do that stacking that I talked about, helps reduce noise. And we get our stack trace. And so in this case, we've got 10 different traces. We've stacked them all together. So that's a 10-fold seismic trace. And so that helps us improve the signal to noise ratio. So this is what it looks like with actual seismic data from our CMP gather, where you can see a very strong kind of hyperbola down here from our first reflection to other reflections. We've got some noise in this upper right-hand area. We do that normal move-out correction to account for the change in velocity. And then we often apply a mute to the data that's further offset where it's a bit noisier and not giving us good information. And so we then sum all of this together. So I don't know if these are like how many different seismic traces they are. And that gives us that one single trace for that pink line. So a lot of information goes into just one seismic trace, one seismic wiggle. And so we can look at these concepts in a little bit more detail. And I'll go through these now a little bit slower. I just wanted to show you the general process to start off with. Okay, so I talked about normal move out. And the way this works is pretty much by correcting for velocity. And so this correction is very, very essential. In terms of stacking, so I've already gone over that a little bit. In this case, from the Hart textbook, we kind of see an example of where we have our signal, and then we have random noise that we will collect also. And so the more stacks we have, the better signal we'll get with reducing the noise, which ideally is not coherent and will cancel each other out. And so this is a case of an example that he made where if we stacked 5 traces over here, we can see the signal, the coherent signal or that reflection fairly well. Nothing I would be super confident in terms of interpreting. Once we have a stacked n of 10, that signal really jumps out quite a bit more, but I would still honestly maybe pick this upper signal, kind of upper peak, as another potential reflector. And then with our n of 20, we've got an even better signal to noise ratio. And so that's kind of, in general, how it works. So you could kind of think about it as averaging out that random noise. All right, so the common midpoint method is one of the key things we have to keep in mind to increase our seismic fold. And so this diagram kind of shows you how you can take multiple source receiver pairs that sample that same subsurface point. And so the more of those you have, the more of them you can stack together and give you a greater fold. And so this allows us to combine all those multiple traces and improve the data quality. I talked a little bit about how we need to bin the data. And so this is just an example of trying to find all the midpoints on the left-hand side, and then you create bins around them. In this case, it looks like 25 meter by 25 meter bins. And so this just helps us manage the data and then also ensure that we have fairly uniform coverage in all of our bins throughout the seismic survey. And then all of those, any midpoints, common midpoints that exist in one bin will be stacked together. And so you can see that from the different data points in B, and all of those get stacked together to just form one wiggle trace in the post-stack data. So image quality will also depend on your choice of stacking velocities. And so getting a good velocity model is very, very essential, very crucial. Sometimes it could be hard to do if you have very complex geometry, very steeply dipping geometry, or features. It can also, be complex, more difficult to do if you don't have a lot of well logs in the area, maybe if you're working in a frontier basin. And so this is just an image that shows the difference between having correct stacking velocities on the left side in part A, but in part B, those velocities have been altered by about 10%, just to show you how the image becomes a bit more coherent with incorrect velocities. And so you could see some lovely cliniforms up here in A, and those are much harder to interpret and they look much noisier in B. This is an example also of the effects of fold in the seismic data. So here we've got 15-fold data on the left, 30-fold and 60-fold, 50-fold data. And so you can see that the noise is much reduced as we increase the fold. So I think it's pretty obvious to tell that we would rather have higher fold data to interpret off of, particularly if we want to be very confident in our interpretations. In terms of normal move out, so this is correcting for the natural move out of the reflections with offset distance. And so here's a CMP gather before on the left and then after NMO move out. And so you can see how applying the velocities corrected that hyperbolic shape into a flatter horizon that will be easier to stack. There's a lot of noise that ends up being recorded, and so this is an image from the Beacon textbook that shows all the various types of noise that you'll see in seismic data. And so understanding these different noise patterns, it's good to just be aware of them in case you come across them in your seismic data. Typically, in most modern seismic data that's processed by a industrial processor, they take care of a lot of these issues. And so this is an example with land seismic data where we see reverberations from the energy. We see the ground roll being recorded. You've got air blasts from the acquisition method they were using. We've got harmonic noise. There must be some sort of facility nearby, and so that's creating some noise. And then nearby vehicles. So, and even if it was a windy day, you could get noise from the wind. So with a lot of what I'll be showing you in these lectures, we're going to be talking about full stack data. And this is typically the data set that probably 95% of us start out with interpreting, because full stack data includes all the angle offsets. So it has the greatest amount of fold. And they're really great for structural interpretation. And they are even pretty good for stratigraphic interpretation. And you can even do some work with direct hydrocarbon indicators on full stack data. You could do better work with angle stacks or gathers, but we'll talk about that in many, many lectures. In those cases, we often want partial stacks to get that extra information from fluid indicators. And so those partial stacks that we may be interested in are where we sum traces that have a very specific angle range. So you may have heard of these called like your nears and your mids and your fars. And in those cases, our nears are angles maybe from 0 to 10 degrees of reflection from the vertical, and all of them are stacked together. Whereas our fars may be more of the angles 20 to 35 degrees, and you can even have your ultra fars. And so those can be stacked and created. If you have the gathers, you can stack them any which way you want. There's actually a lot of pre-thought that can go into how you stack, depending on how much you know about the reservoir that you're looking at, and you can choose the best angles to do so. So you don't always have nears that are 0 to 10, mids that are 10 to 20, and fars that are 20 to 30, but those can be adjusted if you have that original data. Okay, so we've covered some of the concepts and processes for stacking seismic data, and so I kind of want to go over now some of the other things that we do prior to stacking the data. These are things such as correcting for amplitude loss with time. So as our energy goes through the earth, we lose some of the amplitude, and we may want to equalize that from along depths. Other things we have to do are correcting for elevation changes if we're doing land acquisition. We also want to minimize the effect of the wavelet. So that's a process called deconvolution. And then other things that are done in the pre-stack processing phase are determining the optimum velocity function for stacking. And so there's a lot of other processing steps that can be applied, but those are some of the main ones I want you to be familiar with. And one of the biggest kind of concepts that's really good to understand is the concept of migration. And it's pretty difficult to understand, but what migration is in a very simple way is it's trying to take the midpoint where you have that reflection and put it in the right space three-dimensionally. Okay, and so we know where the source is, we know where we recorded it, and we know how long it took to go from the energy took to go from the source to the receiver, but we don't know exactly where it is where it reflected in the earth. And so that's the process of migration. Okay, so the way migration works is the first thing we want to do is we want to try to find any possible reflection points. And so we can do that for any travel time source receiver pair, and you could think about it in that it could reflect anywhere kind of along a semicircle, as I'm kind of showing here. And so you can calculate all those possible points of reflection in the earth where it could have occurred. And so you've got that ellipse of possibilities. And so each travel time measurement, so each source receiver gives us one ellipse. And so What we do for migration is we use multiple receivers. Okay, so we have thousands of receivers. We can have all of those ellipses of possibilities for those source receiver pairs, and we can line them up. And then that helps us figure out exactly where they are reflecting. And so that's Huygens principle is what allows us to take all those ellipses and line them up to realize where the reflections are adding up constructively. And that's the true reflector position. And so everywhere else, they tend to cancel out. All right, and so I kind of tried to put together an analogy for this. To explain it better, I like to teach in analogies a little bit, I guess. And so one way to think about it is you have multiple witnesses that describe an event. So we witnessed a crime. And so one witness gives a little bit of a description, but it's a bit vague. So that's our one ellipse. And then when we talk to the other witnesses, we collect their ellipses and their descriptions of the events. And so where their descriptions tend to overlap, that's where we likely have the truth, or in our case, the constructive interference, so the location of the reflector. So hopefully that helps. It makes sense a little bit more. And so one of the keys about migration is that you just want to make sure that you have enough data, because the more data you have, then the more accurate velocity information you'll have for your travel time calculations, and the better migration you'll be able to do. So migration is super critical. It's kind of a common processing step nowadays, but it's really good in cases where you have more complex structures like salt domes and steep faults or thrust belts. It's really great where you have a lot more velocity variations, so things just aren't steadily changing with depth. If you have lateral changes in your velocities, gas chimneys, carbonate bodies. And so overall, there's a lot of key benefits to migration. But like I said, nowadays, almost all of our data is migrated. But you can still see migration artifacts in some of your data. And so this is an example that shows unmigrated data on the left versus migrated data. And so we've got kind of this, it looks like a folded feature. And it's much harder to see in the unmigrated image. You can see it's a little bit blurred than it is in the migrated image, where we can image that kind of fold a little bit more clearly. And then here's another case for 2D unmigrated on the left versus migrated on the right from Liner's textbook. One of the things we often talk about noticing if we have a poor migration are, these kind of like upside down smiley faces. So you can see them a lot more on the left side. I'm trying to trace out a few of them. And that's a very typical artifact that we see in unmigrated data. It can also, you sometimes still get these diffractions a little bit in migrated data. If you see them, like this is not geologic information. And so these are things you want to be aware of so that you don't incorporate them into your interpretation. So with seismic processing, you can get many, many different products. You could get handed a file folder, digitally, of course, probably, that has a whole bunch of information from your full stack, your gathers, different angle stacks. You should always try to get your hands on the processing report. There may be different parameters or different SegWi files that come out at various stages during processing. And those are all things you want to keep track of. But if you had to go through them all, it would take a lot of time. So if you're a seismic processor, or you're supposed to be QCing it, it's good to go through them all. But if you're a seismic interpreter, you want to think about which ones will be most useful for the purpose that you're interpreting. And so here's just an example of a seismic processing flow just from a paper that I found. And it shows like these tend to be fairly similar, but they may have different stages in them. And this will be information that will be available in your processing report. So you can see here we've got a couple of different inputs, which would be the original tape data, the raw data. It typically goes through some geometry kind kind of like a geometric process to put all the data in the right place. You may do some amplitude recovery stages, some filtering, some deconvolution to remove the effects of the seismic wave. You'll often see that people do static corrections, other types of dynamic corrections, and the types of filtering and scaling that are done are usually detailed in your seismic processing report, often with showing an image before and an image after, so that you as the geologic interpreter can understand how much did the filtering or the scaling or the different processing change the amplitudes or change the structure. So you can keep that in mind when you're interpreting. And then in this case, they did a few different processes from pre-stack migration. So they migrated the data, put it in its right place before stacking, but they also did a post-stack migration, which is where they migrate the data after stacking it. So it's quicker to do. It's often very, very common also because it's easier to do a migration on less data, because the stack data, you've combined all those traces into one. So post-stack migration data is still very good to use and very common. And then it looks like here they also did some sort of zero phase transformation. So in all of these cases, they filtered, they did a stack. So down here, so they've got a stack. So in this case, they were delivered quite a few interpretable products from the pre-stack time migration to the post-stack time migration to stacked data. All right. So that's all time migration, but you can also do depth migration. And so this is where you correct the velocity for depth first, or you correct for depth using the velocity first before migrating. So again, this is doing a lot of extra calculations and processing on all of the unstacked data. So a lot more data that has to be has to go through the processing. So it takes more time. It takes more money. So, but it can be very useful, and it's pretty common, honestly, and very important in areas where you have more complex geologic settings like salt domes, volcanoes, areas that have a strong lateral velocity variation. So just keep that in mind. I mean, if I had a choice between depth migrated data and time migrated data, I'd pretty much always choose to interpret on the depth migrated data. All right, and so here's just an image showing, I've already shown this image before for a different purpose, but just showing the post-stack time migration on top. So we did the migration after stacking the data. Okay, so typically a first product. Then we've got our pre-stack time migration. So we did the migration before stacking the data. And then we've got our pre-stack depth migration. So we stacked the data in depth and then migrated. And so you can see there's quite a bit of difference between the post-stack and the pre-stack images in terms of structure and stratigraphy. There's a few subtle variations between the two pre-stack migration images that you're able to see. But both of these would be great to interpret on. And then here's one more example showing different types of depth migration. And so this is something I'm not going to talk about very much, but there are folks out there who spend a lot of time improving the way we migrate our data. So improving how we track where in the subsurface that energy has traveled. And so one of the most basic ones that you hear of is Kirchhoff migration. There's also wave equation migration, there's control beam migration, and there's more methods also that have come out. And so you can see that all of them give you slightly different images. And so depending on what you're trying to do with your seismic interpretation, you may want to think, if you have the choice, of what type of migrated data to use. So I mentioned before that there's some other processes that can be applied. One of them is amplitude recovery. So our energy is of the original seismic wave goes down. It decreases as we get deeper in the earth. So oftentimes we do some sort of amplitude recovery Something like automatic gain control is a very common method to try to compensate for the energy losses. And this is an example here where we've applied AGC on the right-hand side. And so you can see a lot of the reflections much more clearly because those amplitudes deeper have been up. Those amplitudes have increased. I mentioned before static corrections or correcting for land or ground elevation. So this is very common for land acquisition, because if you're shooting survey and you have a difference of a few meters on the land, that's going to affect the time your energy is recorded. And so in this example, you can see that energy that's recorded. So if you had a receiver at the top of this hill, it would take longer for the energy from your reflector at depth to actually record it, even though that reflector should be flat. So you want to do that static correction. Deconvolution I've mentioned also. So this is a process that's essentially used to remove the acquisition energy wavelet and transform it to that zero phase wavelet that we prefer for interpretation. And so this is an example of deconvolution. So we've got on top without deconvolution, and then on the bottom with deconvolution. And you can see that there's, it looks like a little bit more continuous reflectors that we'd have a little bit more confidence in terms of mapping once we've done the deconvolution. And so just to wrap up, there's a lot of concepts that I went over in this little mini lecture that should take a semester. I know at OU it will take a semester next year, so it'll be a semester-long class. But there's a lot of steps in the basic processing workflow, and there's some very critical processing steps. And so just knowing and being aware of what these terms mean is really important for the interpreter. Knowing the different data types, the data products that you want to work with, from the full stacks to the angle stacks, is another good thing. And I'll be talking about a lot of these later on in the course, as well as if you're working in the time domain or the depth domain, and how has that data been migrated. And so just a few other things that you can pause and read over. I tried to put in a lot of highlights, but a lot of this all goes down to quality control and how much confidence we have in the reflections when we're doing our seismic interpretation. So thanks for listening.